All right, guys, so had to restart a few things. We'll see if it works this time. Maybe, maybe not. It came up pretty nice. Okay, maybe someone signed off. Sorry about that. I'll piece together the videos, so hopefully you didn't really even notice much of a lag, much of a whatever. But as I was saying, so cross sections, remember, we're trying to accumulate through integration, combining all the areas to find the volume. I mean, usually we combine infinitesimally thin areas of rectangles, so really we accumulate lines to get area, which is kind of weird, but now we're accumulating like paper thin slices kind of to get volume, which is still kind of a weird idea. But I mean, you guys have seen like reams of paper. It's tons of very thin pieces of paper that can be accumulated to make like a width or a depth. Kind of the same idea, except in calculus, like, no, we're making them infinitesimally thin, AKA no depth at all to add together, which is the crazy weird part. But I'm gonna go ahead and switch to, if it lets me, some cool illustrations. So there are on Wolfram Alpha, there are lots of cool illustrations as to exactly how this works. As far as just the idea of Riemann sums and where we started with integration and how that now applies to volume. Let me see if I can get over to where those guys are. Here we go. So starting off with Riemann sums, a simple illustration. I mean, I can choose any curve. I have a sine, I have a cosine, I have an x squared. I can make the region that I'm looking at be longer, as in having more area, except that problem is like sine and cosine are stuck between 1 and -1, so it's a little bit easier to see. Let me have this not go quite as far, because otherwise you guys will be like, sine's just 0, no big deal. Okay, I should say cosine 0. Sine's definitely not, look at all that positive area, but the idea is, okay, 4 rectangles, okay, it's good. 3 rectangles is worse, 4 is better, but as you keep fitting in more and more and more and more and more rectangles, which we never actually went up to having to do 38 rectangles, as you can see on the screen, but we did think about the limit as n goes to infinity, like the error is going to get smaller, like there's tons of error back here, look at all that white space. But here you can barely see any, like for all practical purposes, or as you think of the idea of a limit and it's converging, it's approaching, I'm having infinitely many fit in, like I am in a sense accumulating, even though there's still error, look at it, it's still jagged on the top technically, there's still error, but if I go to 1,000 or 1,000,000 and I see that it's getting like 0.0, 0.000, 0.0000, well, the sum in this one is 1.55555. If you guys didn't see right up here, it's actually showing you what it's going closer and closer to. So way down here, it was 1.37, and now it's 1.5 and 1.55 and 1. There it goes. Oh, well, no, 1.57, 1.58, 1.59. What could that be converging to? You guys, well, 2.18655. I'm not sure exactly what that is. Pi over 2 is probably a nicer one that they had us start at. Now all these are decimals. But you could theoretically take the antiderivative of sine. You could plug in, okay, this nasty decimal -0, and you would get what it should actually be. So Riemann sums, we were accumulating rectangles. Let me go ahead and get rid of that one. There we go. Let me go ahead and go find another one for us to look at. How about, here we go, approximating volumes. It's kind of the same idea. I could do different shapes here. I think I have a sphere, I could have a cone being fit in, or a Steinmetz. Let's not do a sphere because that's more the rotation idea is coming in 6.2b. A Steinmetz would be fun. Let's do this one because there's no rotation. There's squares on this one instead. So the idea of this, like I could actually like, play around with it and I could rotate it and you guys could see what's actually there. Like these are blocks, but do you guys see how the edges are all jagged, right? But as I include more and more and more layers, this time I'm taking slices, but I'm making the slices thinner and thinner and thinner and thinner and thinner. And we start to see what this Steinmetz is actually supposed to look like if it was thin, if it was infinitesimally thin, if it was smooth and it wasn't all jagged. Yes, it's still jagged. You guys can still see those jagged edges. But man, it's a lot closer to what it's supposed to be. It might be a little bit easier if I use a cone because a cone is something that you guys know what it's supposed to look like. But still jagged edges, right? But the more layers you fit in, the closer you're going to get to the actual volume if that was smooth. So then think about, okay, well, what are these layers? Because we can't do what we did last time. What we did last time with integrals was accumulating two-dimensional rectangles with bases. Okay, that was like dx or dy, and then heights, and that was f of x. So we put in an integral, an f of x dx, or an integral of f of y dy, and it would be like a rectangle, but we're really just looking at like the one-dimensional height. But this time we can't just look at like a height. I mean, these are actual like cylinders for this guy, or for the Steinmetz when we were doing the squares. Those are actual like squares, but not squares, not two-dimensional. They're three-dimensional like rectangular prisms, or in this one, they're actually like cylinders that are being added up. So we have to set up our integrals a little bit differently. I have one more that I was going to show you, one more illustration, and that just gets a little bit farther into this idea of cross sections. And this one, you can see kind of just what the shapes are. Now, the very base of this is something that we're pretty used to. Like, we're used to seeing a circle. I mean, not tons and tons because it's not a function, but this year we've seen a circle a few times. So we have a circle, right? And then coming up out of that circle, which is weird because what we used to look at just like on a graph on our paper is actually going to be the basis or the foundation of the shape that's picking or coming up out of it, kind of growing up out of it. Last year, the guys were talking about like different marble people that would grow up out of the ground. There was some guy who was like a water puddle or something. Anyway, but growing up out of it. And I think that video that I have assigned for you guys to watch on Google Classroom from Edpuzzle is going to kind of help you visualize this as far as having this shape be down on the ground and something growing up. But it could grow up in squares. It could grow up in equilateral triangles. It still has the exact same base. So it looks very different when it's growing up in triangles or semicircles. It's going to look totally different, or rectangles even different. And we could have that base be something different, like have it be a square, and how would that look? Which, I mean, that's really weird. Shows, and I don't want this to be a shell. It's actually supposed to be solid. But if you're going up out of a square with semicircles or equilateral triangles or squares, or if you're going up out of a triangle, what would that look like? Or if you were growing up out of something that was linear on one side and curved on the other, like that would even be weirder. But we just start to have all these very unique volumes that we're able to find. This is an oscillating one, like a sine and cosine. We could kind of get like a vase in a weird sort of way, which is kind of crazy. There's your bottom. But growing up out of it could be, I think this one's squares, right? Because I can see the square. Could be squares, could be equilateral triangles, could be semicircles, could be rectangles. Anyway, super unique. There's like your vase, right? Super unique volumes that are able to be found by calculus. Let's get back into our notes and let's figure out, okay, so what's going on with the calculus? How does this work? Once again, I think the video I've posted for you guys to watch will help as well. And let's see if it continues to work, and I hope it does. Okay, so we've had a lot of introduction into this idea. Let's try to figure out the actual math. Really, there's one forever card that I already showed you guys. It's already online if you want to go check it out. There's one forever card that describes this whole thing. Like, it's short, it's sweet. It's literally volume equals the integral of area. But how does that work? Okay, you guys can kind of see it here. I haven't technically made it a forever card quite yet. At this point, it's coming later in your notes, but you have two expressions that say, hey, this integral of a of x when the slices are perpendicular to the x-axis, or the integral from a to b of a of y when the slices are perpendicular to the y-axis. We have these two formulas, and you're looking up above, and you're seeing some slices that are literally perpendicular to the x, some slices that are literally perpendicular to the y. Let me go ahead and try to at least somewhat build this idea of, wait a minute, you were showing us like fragmented kind of like jagged edges, and right here, these look totally smooth. So what's different? Well, in these ones, they're trying to show you kind of the idea of what the integral does. But in some sense, you kind of lose some of the idea, some of the concept of what's really being included, like for instance, in this integral from a to b of a of x dx. Because down here, with the a of x dx, you have this dx who's actually signifying, remember how volume was the area of the base times the height. So for like a rectangular prism, it was length times width, area of the base times the height. Or for a cylinder, it was pi r squared, area of the circle times the height, pi r squared h. So volume is very commonly in our geometric training been area of the base times the height. So you're looking at this integral and you're seeing an area That's what A of X is standing for. You're seeing area, but you're not necessarily seeing the depth. There's like a dx, or in the next one there's dy. But if I come up here and if I try to show it to you, maybe it'll make a little bit more sense. Because technically this should be a bit thick. It should be a slice. It should be a slice that we can see, a slice that we can pull out, a slice that we can touch. This is a slice that has depth. Now this one, okay, because you're rotating, that slice is going to be kind of smooth. But if I was to give this guy a slice where it came straight down, straight back, straight down, if I gave this guy a slice, it would not be smooth and in line with the figure that you have. It would be jutting out, kind of like you guys saw a little bit ago in those ones that I was showing you. This slice would be, and if there were lots of slices of squares on top of each other, they would be more jagged, because then the next one would have to start just a little bit apart in order to get that next one. And then you might be able to see that jaggedness just kind of start to form, and the next one would be, okay, a little bit separated from that, and then you would start to see that jaggedness form a little bit more. But in each of these, let me get rid of some of those slices I was putting on top of each other. In each of these, there is a thickness component, and that thickness component, check it, that thickness or that depth that gets us from the second dimension into the third dimension, looking at the screen, this one is a change in x for this specific one that would go into a dx into our integral. So delta x is a change in x. If you see, it's a horizontal change, because here's our x-axis right here. It's a horizontal change that in our integral would be a dx. But if you go look at this other one over here, this is no longer a horizontal depth, this is a vertical depth. With it, in these pictures, it can get a little tricky, because if they start putting like our x, y down, then it's a little tricky. Who's x, who's y, like where did it get twisted? But you can see right here, there is a thickness. The thickness this time is a vertical thickness, and that vertical thickness is going to be a change in y, which we can show by dy. But with these thicknesses, the orientation of the slices is going to lead us to a dx integral or lead us to a dy integral. And that's different than 6.1, because in section 6.1, remember, we were thinking top, bottom, right, left, which orientation makes the most sense, and we had to make a dx or a dy as a result of what we saw. But sometimes we could do it both ways, just one way is easier, one way is harder. But as we're looking at these ones right now, as far as the volumes, it seems to be kind of set as to which way we're supposed to go. Now check it. If you look at the orientation of this slice versus the orientation of this slice, one of them is dx, one of them is dy. Is there a way that we can remember this? And the answer is yes. As you guys look down here, and remember, building up to that forever card, as you look down below, maybe you could be putting this in your notes, maybe you're just kind of following along, because these figures do get a little hard sometimes. If you guys are looking, you can see this idea of, hey, perpendicular to the x-axis, perpendicular to the y-axis. If you've already watched the video, you saw that I put a note in there about like, ooh, the question should have been a little more specific and told you how it was sliced. If you guys check out this guy, here's that x-axis going through, and if you notice, the way that this guy is oriented is up and down. That's hitting the x-axis at a right angle. Hopefully that shows up for you in just a second. The orientation of the slice is up and down, and if you were a knife making that slice, you would be slicing perpendicular to, at a 90-degree angle to the x-axis. Hence this first one in terms of x, and hence also this thickness, that's the dx. Now if you look at the other guy, he's slicing the other direction, and so that slice perpendicular to the y-axis instead, if I was to look at that y-axis, there we go, there's that right angle. That slice that goes that perpendicular direction is always going to lead us to that dy, as long as we're accumulating slices, and that's how we're doing volume, which are what these formulas are both built upon. But if you get the concept of when is it dx, when is it dy, am I slicing this way against the y, and so it's going to pop up in a dy fashion like you can see on the picture, or whether it is the other direction, I'm slicing perpendicular to, I'm trying to get my pointer, but it's not coming up. I'm slicing perpendicular to the x-axis now. And so with that slice, I'm going to pop out, and that out is going to be a horizontal depth, the dx. If you can get that idea down, all you need to ask yourself then is, do I know the area of shapes? Do I know the area of, check out the first one, do I know the area of a circle? It's a circular cross section. Or the next one, do I know the area of a square? It's a square cross section. Now, this one's a little awkward. Do I know the area of a semicircle? But hold on, isn't that just 1/2 the area of a circle? Isn't that just 1/2 of the semicircular? And I think it might be behind my face, sorry guys. But 1/2 of pi r squared. And then the third one over is just another circle. So you have multiple circles going on. But other weird shapes can pop up. Rectangles can pop up, except rectangles, you would actually need them to tell you how high to make it. Base times height. Square is the same either way. You only need one dimension and that's squared, or a circle is built on a radius. You only need the length of a radius. But rectangles need a base and a height. Triangles need a base times a height, unless you have equilateral triangles. That's a weird geometry formula. If you watch the video, you'll notice that I want you to actually go find it. There's also one for an isosceles triangle too, also a weird formula built on basically 1, 2, √3 triangles, or square root of 2, square root of 2, 1 triangles, which are those special 30, 60, 90, 45, 45s. Anyway, all I have to say, like, you just need to ask yourself, do you know the areas of shapes? And that might seem a little weird as far as a statement, but if you notice, both of these integrals just say, what is the area? What is the area of the slice? And then, okay, do I make it dx or dy? But oh, here's a dilemma. If you make it dx or dy, all of a sudden, you can't just stop with your areas and say, oh, I know geometry and I know the area is like pi r squared, because r is not allowed to go in the integral. I have to have an x, and somehow I have to think up here in these shapes, wait a minute, where's r and how does that relate to x? Or in something like a square, oh, it's side squared, no big deal, except, ooh, I need to get that side squared in terms of y. How do I use a y to describe the length of the side? Okay, so there are some weird things that we definitely need to practice, and so let's go ahead and get into some more practical problems. So here's the idea of slicing, kind of a quick summary. If you guys didn't write down the other pictures, try to write these ones down. I'm going to try to show the edges a little bit clear. The slicing, the direction that you slice determines whether you're integrating with respect to x, which is going to be that dx, or whether you're integrating with respect to y, which is going to be that dy. As you guys are getting that down, as you're maybe showing your pictures, I'm going to go ahead and try to make these thicknesses pretty apparent as far as the depths. Because in my mind, and maybe that's not everyone, I'm a visual person. In my mind, it's helpful for me to visualize the slice and to think about, okay, how is it popping out? If it is given a depth, is that popping out in a horizontal way, a dx way, or is that popping up and out? I should say up in a vertical way or a dy way. So right now, this one is a horizontal pop out. That's going to be a dx, and I need then to have that area be in terms of x. Whereas the one down here instead, and this is a little bit weird because this one I actually kind of have my x here and I kind of have my y being the vertical axis. Apologies for my orientation being a little funny. But in this one, just trying to help you guys visualize what it might look like if it was going in terms of y instead. Remember, kind of jutting out, because that's just going to be the name of the game. So it's an approximate. The integral is what makes it smooth. The integral is what makes it perfect. But if we give this guy thickness, this thickness is no longer horizontal thickness. Check it. This thickness, it's popping up. That's going to be a dy. That's a vertical thickness. But if you notice, once again, we can use that. And if I were you, I would definitely write that. That trick of this is being sliced perpendicular to the x-axis. And this one's being sliced perpendicular to the y-axis. So there's that wording again that's going to be really helpful as far as if I am slicing perpendicular to the x-axis or if I'm slicing perpendicular to the y. Okay, pause this page if you need some more, but I'm moving on because this video is already getting way too long with all the technical difficulties. So main idea, 3D figures generated by translating, or accumulating is actually a much better word for that. Translating, okay, sure, but technically, I'm going to zoom in on that. Technically accumulation, well, that's one way of doing it. Accumulating a region of area or an area's region A, a cross-sectional slice through a distance H or through a distance W. That's also known, like our bounds is going to help. That distance we're going through is the bounds themselves. And so we don't actually have to do that. The integral will do that for us, which is what brings us to this forever card. Up on the screen, it's a little bit messy. I apologize for that. I think that forever card is, if I was to, I can look at it on my computer behind me. I have all my computers open. I think it's forever card number 44, if I remember right. And you guys are getting that one down, maybe pausing it as well. I just don't want to put a number on it and then be wrong, which would be a bummer. Let's see, what do I got? There we go, our forever cards. So cross, you guys see that wording perpendicular to the X, perpendicular to the Y. The forever cards this chapter, they are very visual. So to be honest, if I were you, I might actually pull one of those illustrations up above that helps your brain think about the DX or think about the DY a little bit clearer. The only problem is that the shapes are going to change. Since the shapes are going to change, you can't just draw the ones that look like rectangles or the ones that look like circles or the ones that look like triangles. Like the shape's going to change. So there's not like one set, oh, hey, this is it every single time. But there is going to be some sort of region, some sort of like section 6.1 shaded part that's been put down on the ground. And these shapes are growing up out in triangles or in semicircles or in squares, growing up out of that. Once again, I hope that video helps. I'm going to go ahead and label this forever number 44. I got my confirmation from my Google Slides. Boop, boop, boop. You guys aren't here to give it. But that's forever number 44. So you guys can get that down. We are just so close to being done with our forevers. And then we're going to go ahead and go to some examples. And let's see if these examples can help some things make sense. There technically is even a link, I think, if you guys go to like the PDF. There is a link to some of these examples that you guys can follow, made in Java code, etc. Hopefully, hi computer, come on, come to life. And so here's the first one. Both of these actually are using the exact same cross-sectional base. I can actually, I don't know if it'd be helpful though to put it in my graphing calculator. It might not be, the computer's trying to catch up just a little bit, lagging behind. You guys have a little extra time to get that forever card. The first part of some of these problems, if the picture hasn't been given to you, is just to identify like what the different curves are as far as the different curves that we need to be graphing. Come on, little buddies, time for you to wake up. And this one that you guys are about to see and that hopefully is coming up on the screen, I have it on my iPad, it's just not coming up for you guys. There are two functions. Let me go ahead and try to stop sharing and coming back in. There are two functions that are going to form the base of our region. The base of our region, I can pull up the webcam for at least a little bit to see if it's not going to be super gorgeous, but at least you can kind of see it. The base of our region is going to be formed by these two curves, which are y equals x plus 1 and then y equals x squared minus 1. I'm going to go ahead and try to color code those for you guys so that you can get a pretty good picture of that, in that the x squared minus 1 is a parabola, the x plus 1 is a line. So the line is actually up here on this region. I know I technically shouldn't have it going through that rectangle because of perspective, and I should probably technically have that be dotted just for you guys to see. I'm going to take that away because you wouldn't technically see it. That rectangle would be kind of like blocking it. But there's that blue one behind the scenes. That's our y equals the x plus 1. And then down here at the bottom then is our quadratic. And our quadratic, if you see it right here, there's that parabola. And maybe even you can tell, oh, hey, there's even that parabola hitting at the y-intercept of, and then it could keep on going up here if I needed it to. I just don't need it because it's not actually in my figure. But there's that little like, oh, it's a parabola that's been shifted down 1. And it has an x-intercept of 1. And then it keeps on coming up here to, ooh, there's an intersection point. And there's another intersection point. And if you guys look at this figure, it might be a little hard to see because it looks so different because it's popping up in a square instead of in a rectangle, but it actually has the exact same base region. It has the exact same parabola that's showing on, or that's forming one side of that region. And then it has that line that's forming the other side of the region. I'll try to make this a little bit more precise this time. There's the line. So what's weird is behind the scenes of both of these shapes is actually, if I was to try to graph it, this region that you would have maybe totally seen in section 6.1, where you would have had, okay, whatever, a parabola that's been shifted down once, coming up at 1 and at -1. I have this parabola, no big deal. But then I also have this line that intersects at, let's see, it's up 1/1. So it has right here, it's hitting at 0, 1. It's going up to hit the parabola, and then it's coming down and hitting the axis because of the slope going down 1, left 1, up 1, right 1. Actually probably hits up a little bit more. That's a pretty nasty picture. But in section 6.1, you guys would have been expected to go ahead and find the area between this, which is good and all. And that's a baby part of this problem, finding the area between these two curves, because technically this very, very base foundation is that exact same area that you would have been seeing in section 6.1. But what's different is it's not just about the area, you also have this popping up out into solids. If you guys notice both of these, if I were to zoom in on them just a bit, both of these have thicknesses, here's my x-axis, have thicknesses that are popping out along the x-axis. See that horizontal popping out? There it is. So this guy needs to be a dx because it's popping out along the x-axis. This guy's very similar, and that he would also be popping out. Once again, it would be making it jagged, so it wouldn't be nice and smooth. So that's kind of the point, is that when we approximate, all we can do is the jagged. The integral is what we need to make it smooth. So this guy also would be a dx. Right now, according to what we saw on the page before, we need volume for both of these to have an integral with bounds that we'll get in just a moment. Bounds, I wonder what this is bound by. Ooh, how did we find bounds in section 6.1 if we didn't have them? Intersections, right? We set one equal to the other. But we also need to figure out what the area formula is that we could plug in. And the area formula is going to change the volume, because if you guys notice, this one's taller, but that one's more widespread. So which volume is greater? Well, I don't know. We have to plug it in and see. And what are they exactly? We have to do that as well. We need to figure out, okay, so the difference in the areas of both of these is pretty obvious in the basic geometric sense, because that's us reviewing, right? Squares, if I was to go ahead and let's do a lighter green for my review. Square, area of a square is easy. It's side squared, no big deal. The problem is side squared anything to do with an x? The answer is no. Or if I go over here to rectangles, the area of a rectangle is base times height. Now, this is kind of nice because they gave us that the height is equal to 1, right? So it'd be base times 1. Okay, cool. So A is equal to, ironically, because in this special example, all the heights are just going to be 1. Okay, so base times 1, that's kind of awkward. But still, is B x? And the answer is no. So somehow I need to go ahead and look at my picture, look at what they've given me. Ding, 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 ding. See what they've given me up above and say, how do I use this information? It's a dark blue, you can't really see it. How do I use this information? How do I use what I saw in section 6.1 about how to think about and how to find and how to solve for area to help me fill in this area formula? I need a base, I need a side, and then to square him. Okay, before we cover those questions, we have an intersection here and an intersection there. It's as simple as sitting and go ahead and equal x squared minus 1. You can move everything to one side. So x is 1, 2. I think we've seen this a few times already. X is 2 and x is 1. Where my x's are equal to 1 and awesome, right? I mean, not awesome, but at least I found them. I have the -1 there. I have my there. I have my 2 here. All of a sudden, I can come down. I can be like, all right, I know my bounds because both of these are held in by those natural intersections. I can do that. I can also, if I want to be super snazzy, I can also say, okay, not only do I know the -1, 2, I also know that this guy literally just is base of x, and then the height is going to be 1. So I can actually bring into geometry and be like, okay, somehow I just need to go ahead and figure out a case. Maybe I need a lot of space for that, maybe I just need a little. what I need to do instead is take well, and if I make it 1, 2, I need to square, because it's a square, and square has an area from geometry of side squared. I need to figure out the side and then square. So let's go ahead and analyze each of these shapes. I really wish I had a bright yellow. Yellow. Yeah. If we were to get up here and then look at this square, and actually look at, I mean, I can draw other squares. This is just a representative square. There'd be another square that would be right here. I mean, we'd be a lot smaller. And remember, square, the side which is bound by the curve, this has to be the exact same as this side of the measurement. Okay, that's about right. There'd be another square that would be right about here. Right. The question is, for like either of these squares or any other square, this would be a little baby one. As I go up here, it would get even wider for a while. What defines these sides? What defines the length of how long this side is, which is the exact same measurement, even though it's a different measurement. The exact same boundaries, even though it's a different measurement. The exact same boundaries, even though it's a different measurement. If you guys are wondering why this is a random white thing, it's trying to block the glare from the lights onto the iPad. It's kind of working, kind of not, but we're trying. So anyway, I think that's section 6.1. What marked the boundaries of those slices that I was making? Because that's ultimately what I'm doing. I'm making a slice for the square, and it's popping up into a square, making a slice for the square. Hey, I have a top and I have a bottom. I have a blue that's always on top and I have a green that's always on bottom. So with that, all of a sudden it's like, wait a minute, I can talk about, even though these are two very different measures, I can say, hey, they're both sides that are defined by top minus bottom. Now, who is the top? Let's go get them. The top is the line, and the line is x plus 1. And then, who is the bottom? Well, remember, top minus bottom. The bottom is the green one, and the green one was my x squared minus 1. All of a sudden, I have an expression by just knowing, hey, these figures are stuck within the curve. And since they're stuck within the curve, I can think of top minus bottom and maybe similarly right minus left to help me out, which means when I come back to these forever cards, now careful, it depends on the geometric shape. These A's can be all sorts of different: base times height, side squared, 1/2 pi r squared, 1/4 pi r squared, pi r squared. They can be all sorts of different things, but it might be helpful if you remember somehow you are using that idea of top minus bottom to help you fill in the side, or fill in the radius, or fill in the base of a rectangle, or fill in the side of a triangle. Whereas in this guy, because it's all flipped on end, you're going to be using instead the idea of right minus left, which we don't have one right now. We're only doing some that have been sliced perpendicular to the x-axis. But top minus bottom, right minus left is actually still going to be here, because those areas that we saw in 6.1 are just the bottom. They're the puddle that these figures are growing up out of, or being generated out of. Not spinning yet. Some of them might, but not all of them, but just literally just coming up out of. And so check it. I can literally just go ahead and put this in my integral. Hey, okay, so top plus 1 minus bottom, which is the green, which is our x squared minus 1. That's going to be our integrand. Careful, remember, we have to have side. That is the side. We have to have side being plugged in and then being squared because of geometry. But there we go. We have our side. It's all in terms of x, and that's something I can actually solve. Doesn't mean you'll have fun solving it. It's an integral. Remember, some of them just throw it in your calculator, and some of them by hand. And then this one, oh, come on, guys. You would actually square this, right? You would rewrite it and actually square it. Sorry. You would actually square it if you had to solve it by hand. You would do that foiling, you would do that squaring, and then you would just take it piece by piece, power rule. But what's different with this guy? This guy is the rectangle. This guy is the one that has an area formula of base times height. They gave us that all the heights were 1. But hold on, wait a minute. Even though his figure is different, even though his picture is different, his geometry formula is a bit different. Doesn't his side, doesn't his base, the guy that I need for our base times 1, isn't he also determined by and found by? Isn't his length going to be the same thing? So what was S is now just B. What was top minus bottom is still top minus bottom. It's just this guy instead. So I'm still going to have my x plus 1. I'm still going to have my minus. And I'm still going to have my x squared minus 1. So what am I defining? Time 1 defined base of the rectangle. What was the side of the square is the base of the rectangle. No big deal. They're being sliced the same way. There's different figures, different shapes with different volumes. So I'm going to come on down and actually be able to do the exact same thing for this guy, which is why the book and why even me as well, why we like to show you one set like base region, which is the blue and the green of the parabola and the line in this example, and just show you with different shapes popping up so you get an idea, you get like a natural intuition, hopefully, about how, hey, very little changes. You're using the idea top minus bottom, you're using the idea of the natural intersections, and you're using the idea of geometry and geometry formulas. And remember, behind the scenes, I mean, not that you have to have this perfectly down, but this dx is technically like a little delta x being like, I'm giving you depth, I'm giving you depth. I can't do it perfectly though. I'm throwing you in an integral and letting you make them infinitesimally thin and accumulate. Basically the same thing over here as well. We're giving it depth, but if we were to give it depth, it would be jagged, it would be crooked, not crooked, but it wouldn't be smooth, it wouldn't be perfect. That's why we have to throw it in the integral for those slices to become infinitesimally thin and to perfectly accumulate. Now might be a good time, which I'm a little, well, actually, I'm just using the webcam, which connects perfectly all the time. I was going to say I'm a little worried and I'm a little bit afraid that my iPad won't work if I come back, but just kidding. Just fine. Let me go get those. I have to share my screen though, so that you guys can see it. I'm going to go get those student projects that I was showing you just a little bit ago to change it up, let you guys shake it out, maybe go get some crackers or pause me, and then there we go, come on back. But these projects are ones that calculus kids have made that teachers, and guys, literally, I just searched project. This is a very typical project. But they were able to basically come up with their own spring final project, come up with their own shape that they wanted to make a poster out of. They just needed to somehow use geometric cross sections or slices. You see semicircles for his mustache, semicircles for, I don't even know what that is. Semicircles for, I think it's semicircles for this little like, anyway, that's funny. Semicircles, I think this guy, nope, semicircles. I was thinking maybe rectangles, semicircles, triangles, here we go. We have triangles in that one, triangles in this one. Semicircles usually make the prettier shapes. That's why a lot of people do it. Oh, this one's nice. We have a lot of different ones. I think with the same base region, they might be changing it up a little bit. We have Olaf's nose, that's super exciting. Lots of semicircles, squares, rectangles. They had to choose a cross section that they could actually measure. They had to choose a cross section that they could actually measure. I'm not sure I'm actually showing this to you. I thought I was. Let me try again. There we go. Sorry if I wasn't showing that to you. That's a bummer. I was looking at them and having all kinds of fun. But anyway, so these different figures, these different shapes that they were doing, they had to choose some sort of geometric solid, even though the whole thing put together is not geometric at all. The slices are the rectangles, the semicircles. I was able to find some of them. Oh my goodness, it says muscle. That's hilarious. More squares. There were some, semicircles of like a heart. Those are just going to be circles. Those are squares. I saw somebody who had done, oh, there we go. There's some triangles. They were trying to show a toilet. That's awesome. Anyway, talk about potty humor. Anyway, orange and ding dongs. I should have done ding dongs. That'd be fun. Coca-Cola bottle, that's semicircles. But basically what they're doing is they're approximating with how many slices they've done, because they can actually measure how deep these are. They can measure the radii, or they can measure the sides, and they can actually add up to get an approximate of, they use Play-Doh, an approximate of what the area, or I should say what the volume is. So this one can say like, hey, I know how many slices I made, and I have this curve and I have these depths. Like they can actually add these together and figure out what the volume is of what they've done, and then compare it to what the integral would say, and then show how much error there was. Not that they were supposed to get it perfect. They weren't. It was supposed to be approximation. But that's what, ooh, there's this sliced bread. The Rice Krispie treat would definitely be my favorite, and I would eat it and it would be gone. Anyway, so I was just trying to show you guys the idea of the project is like, hey, if you were to do slices and if you were to figure out the actual geometric dimensions and find the volumes using like length times width times height, or using for some of these cylindrical ones, pi r squared h. If you were to actually measure, if you were to actually add up, you could then just say like, hey, but I know the curve of this. They had to kind of choose figures that they had done a curve, hence like this little sea dragon guy. He was like a sine and cosine. They had to somehow use curves to define, but then they were able to throw it in an integral and be like, hey, I know exactly what the perfect volume is, even though mine was just approximate. So anyway, it's kind of a cool idea. I'm going to come on back and see if I can get my iPad to work so I don't have to be holding it under the webcam. Not, oh well, we'll just keep going. So we're going to do a few more examples of these cross sections. Remember, it's like the beginning. Ooh, it might work. It's like the beginning of your homework. Remember, 70 and 71, it doesn't seem like a lot, but that's why I also put that video in Google Classroom for you guys to watch and get another like intuitive understanding. And to be honest, there are tons of AP practice problems of cross sections. I think we might see a few towards the end of this video, or I might save a few just to kind of put on the 6.2b portion, because this is 6.2a. Anyway, this we do not have to solve, because to be honest, we literally just did. If you notice this x plus 1, x squared minus 1, that's exactly what could have been given to you in literally, guys, just words. They could have said like, hey, if you were given an f of x is equal to x plus 1, and if you were given a g of x is equal to x squared minus 1, my cursor's in the way, it's bugging me. But they could have just said like in words like they did in section 6.1 sometimes, like, hey, you have two curves, and you're like, great. And then popping up out of them are these shapes. Are these squares? Are these rectangles? And you're like, double great. The awkward part of rectangles, remember, or at least kind of have in your mind or have in your notes, the awkward part of rectangles is that they do, because of that base times height. Square says, I only need a side, and that's awesome. Rectangles say, I need a base and a height. They have to either give you a height or give you some sort of, I'm just going to do that, some sort of clue about the height. If they don't give you a number, it has to be like double the base or triple the base. They have to give you a clue, because you are only able to show one dimension with that top minus bottom, or if everything was flipped, that right minus left. So they have to give you some sort of clue about like a height if they were to bring in a shape that has more than one dimension. A circle, 1/2 pi r squared, or pi r squared semi or full. R is all you need, so R is going to somehow come from top minus bottom, right minus left. For equilateral triangles, it's side, 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 so that weird geometry, Google it. Formula only uses a side, top minus bottom, right minus left somehow contributes. Anyway, just the ones that have like base times height or 1/2 base times height, there has to be a way to relate, or else you wouldn't be able to solve for it. Let's get past that example and let's go to something else. Ooh, equilateral triangles. I don't want to give that one away to you. You're supposed to see that one in the video. Let's do number 60. Let's do semicircles. And I don't even think this is number 60 in your guys' book, but it is number 60. This one, we're going to follow the directions specifically, even though technically some of you at the end might be like, couldn't we have sliced this one the other way and it would have been the exact same thing? But let's go ahead and slice this guy. And as we slice this guy, we are slicing perpendicular to the y-axis. So slice, there we go, perpendicular. Ooh, nope, that's the x-axis. Let's undo that and let's slice this way. Okay, as we're slicing perpendicular, you see the y, right? Perpendicular to a right angle, perpendicular to the y-axis. There's the y, and then I form the right angle. We are supposed to remember this circle is just the base. It's the foundation. We're supposed to grow into the dome or grow into these semicircles. So I'm going to go ahead and grow. Not that you have to be able to draw this perfectly, but it helps my brain be able to see, hey, a semicircle with, wait a minute, where's the radius of this semicircle? Because the radius isn't this whole thing down here at the bottom. Isn't the radius only half of it? Isn't the radius only a portion of it? Now, if I zoom in, maybe you can see this yellow just a little bit better. The radius is only one portion of that entire length across. And maybe I can even get like a little deeper yellow. I don't know, it's not my favorite, but it works. that radius is actually just going to be this part. I could go ahead and get my black shading out if it helps, and I could go ahead and show the boundaries as far as, hey, we have this thickness, and this one's not going to be near as pretty. Oh, goodness gracious. Sorry, my artist, my perspective is not that great. I did not shade this very well. But as we are looking at this guy, and as we're looking at this slice, theoretically, this slice that's coming up, it all just disappeared. This slice that's coming up out of this puddle, if I were to give it a thickness, the thickness would be, and this should have been a lot higher, and then it should have kind of like tapered out. Anyway, this thickness would be, check it, if I was to give it thickness, and hopefully you guys are seeing it somewhat in real time. That thickness is now popping up, not popping out, but popping up. And as it pops up, that's going to be a whoop, whoop, dy. Now think about dy. With dy in section 6.1, if you had dy, you needed to get this function over here in terms of y. So we're going to pause right now. We're going to see this dy, and we're going to be like, oh, crud, I need this in terms of y. Right now it has x's and y's. That's not going to work. So I'm going to go ahead and solve for x. And as I solve for x, absolute value of x is equal to the square root of 4 minus y squared. Now, hold on. Remember, that means this technically has two different functions, a negative square root and a positive square root. And I'm going to go ahead and, I accidentally kind of like flung my notes over there. I'm going to label what those are down below because it helps me if I have some color coding to kind of figure out. So I'm going to make this positive one be green, and I'm going to make the negative one be purple, just because I'm running out of colors. Okay, so if I'm thinking about y's, dy's, now remember, when y equals positive root of x's and negative root of x's, I have above the x-axis and below the x-axis. That's above and below. Positive y's, negative y's. But this time, actually, instead of positive y's and negative y's, what I have instead is this little x guy who's in front. So I have positive x's and negative x's, which means the positive x's are actually everything in the first and fourth quadrant. See if I can get this green to show up, which is going to be over on this side. That's going to be that positive, and then those negative x's are going to be over here on the flip side. Now, if I was to zoom in, okay, green's on the right, purple's on the left. If I was to zoom in, remember, our goal is to get this R somehow in terms of, well, now in this problem, somehow in terms of Y. So if I see what's going on here, well, wait a minute, hold on. I have this one on the axis. The axis is x equals 0, and I have this one on the green. The green is x equals the positive square root of 4 minus y squared. You might want to slow me down a bit because, man, guys, I'm ready to go solve. I know who my r is. My r, or my radius, is equal to the positive square root of 4 minus y squared minus 0, using those boundaries that are up above for what that r region was. And technically, we could have gone the other direction. It would have been a little awkward because we would have been going negative instead. But we could have gone that other way, and we could have gone the negative square root. Well, actually, we would have gone the most positive thing, 0 minus the negative square root, which really would be the exact same thing as what I have down here below. When I come to semicircles, remember, at the core of all of this is that basic forever card, which says, I need volume to be the definite integral from some a to b, we'll figure that out, actually this is c to d, that's in terms of y, of an area formula in terms of y dy. So far, okay, wait a minute, I've actually figured out my radius. This is a semicircle, so the area of, let's go back to geometry for a second, the area of a semicircle is going to be 1/2 pi r squared. So I'm going to put into my integral 1/2 pi. I need my r to be squared and then dy. The cool thing is I've totally figured out right from up here, up above, what my r is that I can plug in, which is just going to be the square root of 4 minus y squared. And now all I'm missing are the bounds. The bounds. Wait a minute. The bounds are y values. The bounds are c and d's. The bounds are how low this goes to how high this goes. How do I know how big this circle is? Do you remember x squared plus y squared is r squared? How big is the circle? Well, the circle is up 2 and down 2. If it's up 2 and down 2, if it's right 2 and left 2, I know my bounds. My bounds are y equals -2 to +2, based on the size of the circle. And now at this point, I mean, if I was to solve this by hand, just because this one is a little bit easier, I would pull out that 1/2 pi just because those are constants. The nice thing is, if you were to rewrite, I mean, come on guys, square root squared is like the happiest day on earth because I can go ahead and take out my square root, take out my squared, and I'm left with, the computer is catching up, it's coming, -2 to 2 of 4 minus y squared dy, which at this point I can go ahead and say 1/2 pi, I'll figure out you guys later. I'm going to have 4y minus 1/3 y cubed, all with the bounds of -2 to 2. Some of you might realize that this is a very symmetric area. So I might also be able to, just kidding, you would be able to, just cut this down in half, which in this case would be here. I could actually find the volume from -2 to 0 or from 0 to 2, and I could double it. I could cheat the system a little bit and not have to, because of that even symmetry, that it exudes. I could actually, if I wanted to be super snazzy, and the AP does sometimes do this, I could say, you know what, I want double, if I can get it, I want double of just going from 0 to 2, because I don't like plugging in a -2. That works too, little sneakers. If I do it that way, my life just gets a little bit easier as far as solving, because I just end up with a pi in front, and I only have to plug in a 2 to be 4 times 2, that's 8, minus 2 cubed is 8 over 3, minus, and then the nice thing is now I just have a 0. And I end up with, 8 is 24 thirds. 24 thirds minus 8 thirds is 16 thirds. I have 16 thirds pi, beep, 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 beep. And you're like, wait a minute, I would have never made that match if I did that in my calculator. Just kidding. Remember, you could have gotten from your calculator a decimal, and you would have had to figure out what the back of the book is giving you as a decimal, and then you could have compared to see if you were on the right track before very possibly going down a very bad road that might have led you to lots of work, but a wrong answer. So remember, use your calculator strategically. I'll be hanging out in Google Classroom during your class period, or at least there'll be a link in Google Classroom to come find me on Zoom, where I'll be able to answer questions. If you guys have a homework problem, I can just, I mean, literally, look at this. This is easy. There's no connection issue. I'll just pull up my whiteboard, guys, and I'll do it the old school way if we need to answer your questions or to clarify, or I don't know, if you just want to tell me about your life and how it's going hanging out in quarantine or semi-quarantine, you can let me know that as well. I'm going to go ahead and see what I've missed as far as examples. We missed a multiple choice question using a calculator. Ooh, I love using a calculator. Another one using a calculator. And then, ooh, that's an introduction to, the pictures. The pictures are about to get exciting. But guys, that's 6.2b. And technically your homework, if I was to, let me get out of my iPad, because I think we'll save those AP questions for another day. If I was to pull up your Google Classroom, this homework is due, excuse me. I haven't assigned it yet because I'm trying to get this video so that it all comes out at the same time. But according to my calendar, this homework is going to be due. Doesn't help you guys because I didn't share my screen, so you're not seeing it, but that's all right. It doesn't really have much info anyway. This homework is going to officially be due, whoa, next Tuesday. Next Tuesday. Today's Monday. You're getting this probably on Tuesday, maybe Monday night, depending on when you check. This homework's due. Okay, pause. I do need a screen share. Because what I need to show you guys is, remember, what we've gone over just now is literally number 70 and 71. And you have the Google Classroom assignment of the video to watch and answer some questions to. Remember, you're getting points for watching it. I can see if you've watched it because you are hooked up with your Heritage Warriors email and your Google Classroom user. So all that to say, the video is what I want you to do next, and to play around with 70 and 71. Start your homework, but you're not submitting that in pictures because check it. 1, 3, 6, 7, 10, 13, 19, 21, 31. All of those need section 6.2b. So if I were you, I would today, and I think on my calendar, if you check it out, today and tomorrow. today and like half of tomorrow, I have as set aside as section 6.2a. So Tuesday and or Wednesday, you guys can just be working on 70, 71 in a video and then kind of take a break from math. But then we're coming back Wednesday, Thursday, Friday. We're going to be working on 6.2b, and that requires even a little more visualization. I'll probably try to find a good video and then assign you guys one of those little ones that'll be due earlier than next Tuesday. Next Tuesday is the book work. But we also have some practice, as you guys noticed, we have some practice AP questions coming. I think I might even take those 2 examples that we didn't do today. I might actually take those and I might post those as little baby, not quizzes, but little baby just kind of like, hey, show me what you can get and show me if you can get it right, like an A and a B, etc. I might actually throw those on Google Forms and see what you guys can do with them on your own because I'm super curious. Or if you guys show up into Google, show up into the live session tomorrow or Wednesday, you can also ask me questions on 70, 71, the video that you watched, or those AP multiple choice that I'm gonna throw your way. So I'm gonna go ahead and add those AP multiple choice to your homework assignment. I think that's the easiest way to do it. So 70, 71, and then those 2 AP multiple choice. Check it out, kiddos, see how you do, get back to me. Love y'all, miss y'all, and this has taken way too long, so let me stop this video, and it'll be shorter next time. Bye.